My talk is on nematodes, which is a term I made up. But in general, it's about worms, how we can use them as benefits, and how to create them, and neat things like that. This is my case history. I'm a researcher with a company based in the States, but with employees all over the world. We do a lot of product sales on a product called Canvas, but we also do quite a lot of training here and everywhere else. And of course, ongoing research as time goes on. Mostly what we do is work on the offensive side of things. I think the last talk was very defensive oriented, and there's quite a lot of companies out there that do sort of defensive oriented technologies, but immunity is not one of them. So I think I didn't want to get too far into semantics, but what a worm is something that people like to hem and haw about, and you can see the small minds of the full disclosure world going on about the terms and what they mean. But in general, I think that anything that inhibits my valid access to porn on the internet is certainly a worm and should be classified as such. I decided to use a biological term, nematode, which is it's a phylum that people commonly put in their lawns to get rid of other pests that they have in their lawns and various other places that they're trying to make greener. And the basic idea is people are quite scared of the idea of using a replicating technology, but I think as you will all believe after this talk, I hope, that there's many good reasons for doing it. So this is my hypothesis, and we'll see if it is true in 3 years from now, Hack in the Box, 2007 or 8 or whatever year it is. Basically, I believe that you're going to see large organizations, organizations that view security as a social problem. Anything from an ISP, where it's sort of a monetary issue for them, bandwidth costs them real money, they're selling something to you at a flat rate. Governments, which obviously have reason to view programs on their network that are replicating rapidly as a problem, because a lot of these networks are sort of government owned, and large companies that for whatever reason need a level of control that they weren't able to obtain with other technologies. And I believe that the simple return on investment of this technology is going to overcome the unreasonable fear people have of deploying it. And that's something that I guess we will all, if your fear feels lessened after the talk, then that's one step toward my hypothesis, but we'll see. So we're going to talk a lot about the reasons you would actually create a nematode. And we're going to talk a bit about the protocols and the structure of a nematode. And I think that the key thing that Immunity has been working on is a way to transform the product we currently have, which is a penetration testing product, into something where you can sort of take advanced control of all that information we have and use that toward a nematode product. And I think there's quite a few other just sort of extraneous uses of nematodes that we'll briefly touch on. People find security quite expensive. They find it a lot more expensive than securing their house. If you look at a company and the amount they've spent on information security in the past year, I think every company in the world is going to tell you that it was way out of bounds. I think, to me, this says that the technologies people are investing in don't work and should be discontinued. And I think a lot of those technologies are things that you talk to a CSO and they're investigating other alternatives. And security turns out to be quite a hard problem. In particular, big companies and big organizations don't have a grasp on the initial problem of asset management, and because they don't have a grasp on that problem, find applying some of the other technologies quite difficult. Hard problems require novel and interesting solutions. I think controlled worms are one of the solutions that people are moving to. Surely we're not there yet. But I think there's also interesting hard problems that are also solvable almost only by worms. And I think the searching problem is something that you look at and you say, I want a document, and let me go search the whole network, and you have kind of a long iterative process, or you're talking to a Google server or something. And I think that there's multiple versions of that document out there, and a lot of these problems are best solved by an intelligence in the network itself. I mean, you're going to hear a lot of the vendors talk about moving the intelligence into the network, and this is in a sense what they're talking about. I think probably the key difference between the way smaller security companies see networks and the way your bigger CSOs see networks is that networks are typically a jungle, especially if you're dealing with companies that are not technology focused, and they've built it from a very simple flat network into an extremely complex network that they've sort of pushed into different branches that they have all over the world, and they've kind of tried to merge it. They don't have these networks documented, they don't have asset management solved, so they don't know what they have. And that makes things like solutions that require a management node on every machine very, very difficult to deploy, and therefore very expensive. And because you're getting companies trying to sell HIDs for anything from $50 to $500 a box, companies just haven't deployed them. They just don't invest in that kind of solution. And I guess the dream, if you talk to these people, the dream is that they're watching movies. They're like, why does my network have some defenses built in here? I mean, the robots in the Matrix are chasing down the intruders. Why don't we have that? I think people move. Then they're like, well, I'll put a scanner in, and I'll scan using Nessus or something similar to do asset management. They're saying, if I just dot these little things everywhere, these little scanner stations everywhere, I will know what my network is like because I'll just scan it every couple days. It's like a radar sweep. And there's a couple issues with that, and I think we list a couple of them here. You're pretty much out of date when you start. You get a lot of these false positives, and Nessus signatures and exploits are not so far apart that you couldn't invest in put another dollar on the problem and get an exploit out of it nearly as quickly. And I think exploits provide more value. Network segmentation is a problem that scanner technology doesn't solve necessarily, because you have to have visibility, and you don't even know if you have visibility. You may not know that your network is segmented, and when you do know, you then have to go pay to put a box on it, or a software agent that can do the scanning for you. And so assuming that you do know, it's just expensive to get your scanners close enough to the targets that they're going to protect that you have visibility. And again, there's that fourth dimension of time where you have salespeople coming in, you have contractors and consultants coming into your organization, you have machines that turn off and turn on. So these things are, everyone says, well, CNN didn't get hacked until some guy came back from a thing, and then they're slammed with the next big LSAS worm or whatever it is. And a lot of this is because the technology they have deals with the fourth dimension quite poorly. They simply can't handle the fact that what's there today is not there tomorrow, and vice versa. This is, I like to think of that as the serendipity aspect of what a worm technology brings you. They bring you the fact that you're like, well, how the heck did the power generator that handles this and that across the Midwest get infected with Slammer? They're like, how did that happen? We can't even see the route that took the worm there. And that sort of unknowing serendipity is the key to what a worm technology brings you. It brings that to you, but from a security standpoint. And I think that's sort of the philosophical stance that we take on a lot of these things. So the other features that you get once you've deployed an nematode is the ability to do searching, the ability to do to move that kind of, I need an intelligence across my network. Now I'm building to this platform. If I can build to a worm platform, I can have sort of a very different kind of distributed computing problem set solved. Exploits and worms obviously are very closely related, but not necessarily indelibly connected. The worms themselves don't need exploits. Testful 1 is a simple Stack Overflow that I wrote one day. But obviously, people are very attached to management agents, and I think that attachment is going to have to go away when they realize it doesn't solve the problem. Because what you really want to manage is the stuff that's not going to be possible for you to manage. You have some developer in some corner who says, I'm installing a Linux box and you can't touch it. And you don't really care until it becomes a problem. When he gets infected with some worm or something, now you care, right? And this is the one of the many things that we hear from people already sort of deploying similar solutions that they've crafted together. But on the other side of it, some exploits are very difficult to write into worms. So you can kind of see the fact that you're like, well, if it's not very reliable, then it won't get wormed. People have this sort of wormability index in their heads. And I think people are constantly adjusting that. They're saying, well, the worm writers of today have an average IQ of 60. It's going to take them 2 weeks to write a worm for the LSAS bug. The LSAS comes out, 2 weeks and a day later, like, all right, look, that looks like I was right. But I think it's actually, especially if you look at Microsoft, they'll often put things in their advisory that are, untrue. Like, certainly it's not possible for this spooler vulnerability to be exploited reliably. It looks like a DOS on most platforms, right? And that's just flat out wrong. So, I'm sure you guys will improve that in the future. Right, good. And I think the thing about that is people need to adjust their sort of wormability index in their head for the ability of people to get smarter over time. So right now maybe everyone has a 60 IQ, but tomorrow after seeing this presentation, they'll have a 61 IQ and they'll be able to write them slightly faster. The real problem with worms that people get tied in a tizzy about is they're like, well, I don't know if I'm allowed to attack something. And this is a problem that you have to solve every day if you're a professional penetration tester. You say, where can I run code that I inject into someone else's machine? And that's perfectly legal to do if they've signed a legal agreement with you. And that can be done implicitly or explicitly. If they've connected to your network, most people consider that implicit understanding, if I'm on CNN's network, that they're allowed to scan my machine. And there's, of course, explicit or implicit. But you can also sign a piece of paper that says you're allowed to scan my machine, and that's what you typically do with a hold harmless agreement. That I'm sure many of you have had companies sign in the past. So I think if you're looking at the nematode problem, you're also thinking, well, this is definitely easier to do when it's me as a penetration tester running a machine. In reality, mistakes do happen, but typically because it's a human being, the mistakes quite easily. You can say, oh, I hacked your web server and you didn't tell me to, so here's how you fix that. And you're like, all right. And again, you have much more, very in-tune knowledge with where everything is on the network. You can say, well, it's called www.bobsfish.com, so it's probably Bob's Fish, right? Of course, nematodes, because they're not working under human influence constantly, do have to work harder to establish this clear mandate. So there's a couple different ways to do this. I think you can rely on an outside indicator to find out where you are, and depending on where you are, you can make intelligent decisions. You can rely on an outside indicator to find out where you're allowed to go. And you can, of course, logging is certainly not something that you really can do effectively, although you can send that off to a remote logging server. And people I think have certainly reached this. Even several years ago, people were using our product and they were saying, I want to automate this and scan my whole network. They're like, I have 4 Class A's. So I need to scan my whole network, and I need, for any machine that is possibly vulnerable, I need to patch it. And I don't have any way to get remote agents on these, because these are all in, these are companies we just bought, and we don't even know their network admin's name. But we know they have problems because they keep emailing us worms. So, this is, I wrote a quick little script here in Python, but this is the sort of thing we see people doing with our product all the time. And I think this is the sort of halfway point. This is people are saying, well, I need exploits I need their functionality. So they will take the functionality we give and they'll build something on top of that that solves a very tough for them problem. And I think in general, I mean, scanners and sort of automated exploit technology saves you money. I haven't gone to the length of trying to buy a ROI paper on it, but I think it's pretty clear from the fact that people are bothering to do it that it's saving them something. And that they do have a clear mandate on their own network. Contact your own legal for that. And of course, this sort of technology has a very large and complex support structure. If I'm going to scan 4 Class A's, there's a lot of framework that goes into being able to do that. And you have the benefit of if I'm using a real exploit, I can use big shell code. I can do extremely sophisticated OS identification. I can go look it up and say, hey, that's Bob's machine. I know when I installed Bob's machine, it was Windows 2000 SP4, and it's French. And of course, network segmentation, you're going to solve it the same way you solve it with the Nessus scanners. You're going to put another node out there. You're going to, maybe try to have the switch tell you whenever a new node comes online. You have hosts popping up. Or reboots and something screws up, who knows what. So this is sort of the story behind the story. I mean, if you're looking at the problem we're solving 3 years from now, we're solving the problem that the solution of tomorrow doesn't solve. And the solution of tomorrow is a good mass exploit scanner. The solution of maybe 3 years from now is something like that incorporates a lot of this sort of nematode technology. And the sort of philosophical thing that we're doing is we're making every host a scanner. We're making every host able to generate scanners. We're having them, ignore things that are not our problem. A lot of, people will tell us, we really only care about your engineer who has his own Linux box when it becomes a problem. It's like an annoyance, but it's a problem when it gets owned. So, if you have these sort of automated, if a scan when it's not relevant stops happening, that's saving you money. But of course, there's technological problems that you need to solve to make this happen. Worms are not easy to write for most people. And even if they're easy to write for some people, those people are not going to chew a big problem like that. Because they're like, well, it took me, a couple days, and I've got porn to look at, so I'm not going to do any more debugging on that. And I think, I guess the sort of computer scientist way of thinking about it is, anytime something's difficult for me to write, I write a compiler for that something. And I think that's the way immunity works a lot. We have a pure Python. I write a compiler for that something. And I think that's the way immunity works a lot. We have to solve, the exploit problem, and now that we have that solved, we can then leverage that against other problems. I think the network bandwidth issue is not as big an issue as it may seem from this bullet, but mostly because the solution is an extremely large and cumbersome problem of developing smart bandwidth allocation between your nodes. And I think there's plenty of computer scientists who'll generate many theses on this in the future, but it's not something that I want to touch right now. The fear factor from the fact that worms are harder to target and control and that they need to ensure legal access. This is definitely something we want to fix, but it's something we want to fix anyway because we need reliability. We have a number of hypothesized ways to fix this. Is the target on a whitelisted network? If we go out and we say, right now, if I wrote a nematode that exploited one of the FreeBSD bugs for the capture the flag, I know that whole 1.10, I think they're using 10.0.0. whatever, I know that that's a whitelisted network. So I can say, go nutty on that network, and then don't go nutty anywhere else. And of course, private address spaces generate some issues where you're like, well, what if I disconnect and then I attach it to a different 10.10 network? And so obviously you have to solve that. I think the way that we prefer is sort of a two-factor authentication method. We'll get into that later. And obviously, if you want, you can install a friend foe system that said, well, if it's showing me that it's a friend, then I know I'm allowed to attack it. So if all I know is that it's sending back a public key or something on a certain port, then I know that, okay, it's mine. Nematokens is a particular kind of server that we use as part of our two-factor authentication method. A nematoken server only responds to requests from networks we're allowed to attack either from or to. So for example, just using a DNS server, I could say, does this exist? And I'm saying it from a network, and the guy says, well, yeah, you're coming from here, and that's a valid whitelisted network, and I know that this from you is a valid whitelisted network, so go ahead, knock it out, I'll return a response. Otherwise, I'll just ignore it. And you have plenty of options for doing sort of a nematoken setup using protocols that can get out. The hard thing about nematokens is you need a protocol that will go through the NAT and still work. I need to say that yes, you all work. I have to have kind of a transparent knowledge into the networks. And so there's plenty of ways to do that. You can play with that. Everyone's nematode implementation, I think, will differ. And so there's plenty of ways to do that. You can play with that. Everyone's nematode implementation, I think, will not be like the immunity implementation. Our initial research implementation, and of course our main goal is that we want something flexible. We're obviously going to build it upon another base, and we want you to be able to say, I'm running a pen test on bobsfish.com, and so after I hit the first box in the DMZ, I don't want to have to go hit every box in his whole network. I want to say, this network range is Bob's Fish. I'm legally mandated on that. Go hit everything in here, report back, and then die off. And here's the authentication token server that you can go to say, what's up. So we're looking for something that's both dynamically created, but also reliably controllable. We're looking for something that operates entirely in memory, and initially, to simplify the issues, we're looking for a single shot. Because we're developing a language here, and we want to develop it with a simple case and then expand it to the wider cases, so that when we realize that our simple case was non-representative, we can shoot ourselves in the foot. So the question, you start developing sort of design documents, and you say, how do we get from vulnerabilities to usable, beneficial worms? And obviously the vulnerabilities go through a process at Immunity already. They go from vulnerability to Python exploit, and then of course then to a nematode intermediate language, a test framework, and a payload that got deployed. For those of you who read the paper on Witty, one of the things he said was, well, his actual framework for sending out the worm was quite flawed. And he's like, most of these worms are not well tested. And it's just difficult to build a test framework around worms. And that's one of the problems you have to solve. This is the generalized problem space. You can if you take a patch and you use bindiff on it, you can generate the vulnerability. If you use binnavi on that, you can generate a repro. From there, you go through Canvas to get the exploit. And then for our nematode thing, you get nematodes. And so this is the basic cycle of life. Or cycle of cache, however you look at it. The thing about where I stand is that we've been writing exploits for 3 years now to a specified API that I think is a fairly good API, and as time has developed, it's become quite rich. And one of the things about that is that when you initially start the project, you're thinking, well, I just want something that works for exploits, but you're also thinking a little bit ahead. You're saying, what language, what sort of features do I want in a language that can aid me to make this flexible for things I can't think of right now? And Python is the language for that. It has the sort of reflexive introspection, sort of the abilities. The language itself is well designed to use in ways you didn't think about ahead of time, and that's something that we were considering when we did the initial design. And so the entire product is written in Python, including all these sort of network libraries that come in. So you don't call socket.send and then here's a big blob of stuff for Microsoft RPC attacks. You send Microsoft RPC connect, bind, whatever, and that gets all taken care of. So that's a good thing, because that means that you have a base of knowledge that you can look at. And you can say, well, what else do I have that will help me do this? And of course, the built-in assembler and compiler is something that will help you, no matter what you do. A simple example exploit in Python, it looks like that. It's got a make exploit, a no ops, a stir override, connect to host, run once. I mean, these are going to change for every person who writes their own nematode implementation. This is probably something that they will do, because it's much easier to write your exploit to Canvas than it is to write your exploit to, just C and then convert it to something else, like nematodes. Basically, the point I'm trying to make here, which is a little obscure, is that if you have a framework, you then have a database of knowledge. It's not just a collection of scripts that run exploits. It's a database of knowledge that you can then manipulate and transform using automated language of some other kind. So this is our nematode workflow. It is that you can take an exploit, convert it to an intermediate language, run it through a testing harness, run it through a specialized compiler, and a launcher. So this is the kind of workflow we envisioned. We have this nematode intermediate language that obviously is under heavy development and is simply a specialized assembly for worms. We already have an intermediate language that we use for the C compiler, and we didn't feel that that was going to be a good representation for what worms need to know. There's just a different set of state that you need to keep. And we wanted something that also was not too hard to parse with PyLex and PyYak, but which right now I don't even bother to use. And again, if you really wanted, you could write your exploits directly to nematode intermediate language, and what you really end up doing is you write them in Python, you test them in Python, you make them reliable, and then you convert them to nematode intermediate language, and maybe you modify them if you feel lucky. So I guess the interesting thing is, how do you transform a good Python exploit into a nematode intermediate language? And we simply, it's actually quite small and easy when you have the right language. You just override the internal API, and instead of generating socket calls and things, you generate prints that print out nematode intermediate language. And of course, you've replaced various structures within that class that, like the shellcode, we don't need that. We're going to replace that with a string, stuff like that. So quite easy to do. I think you could probably do it in C#. I don't know if you could do it in Java. You could probably do it in Ruby, but you probably can't do it in Perl. So this is, we wanted to make it this easy. I wanted to say, I just wrote an exploit. I spent 2 days doing it. How do I make that a nematode, right now? And this is it. Because eventually it's going to get all built into the framework. It'll be nice and GUI and stuff. So, all right, that's right. My mouse broke like 5 seconds before the presentation. But this is me down here. I'll hit enter a couple times. That didn't help. And I say, demo exploit's just a Canvas exploit like any other. It's a really boring one. You can just run it. Do you guys believe me that demo exploit would work? Because I can demo the exploit itself working. But in any case, instead of working this time, it generates this little string here, or this set of strings. It says, I have 5,000 no-ops, I do 2 mem copies. Stir overwrites like a mem copy. I start the loop, I connect, send the data, I close the loop, or close the socket, and I end the loop. So it's a very, very simple thing. And it's human readable for sanity's sake, so that you can say, I don't think that looks right. But this is the worm, this is just a sort of recompilation of the exploit. That was an amazing demo, wasn't it? And so there's plenty of ways to do that. You could, play with that. Everyone's nematode implementation, I think, will differ. I think, as this technology becomes more accepted, people are going to build their implementations, and they will not be like the Immunity implementation. Our initial research implementation, and of course our main goal, is that we want something flexible. We're obviously going to build it upon another base, and we want you to be able to say, I'm running a pen test on bobsfish.com, and so after I hit the first box in the DMZ, I don't want to have to go hit every box in his whole network. I want to say, this network range is Bob's Fish. I'm legally mandated on that. Go hit everything in here, report back, and then die off. And here's the authentication token server that you can go to say, what's up. So we're looking for something that's both dynamically created, but also reliably controllable. We're looking for something that operates entirely in memory, and initially, to simplify the issues, we're looking for a single shot. Because we're developing a language here, and we want to develop it with a simple case and then expand it to the wider cases, so that when we realize that our simple case was non-representative, we can shoot ourselves in the foot. So the question, you start developing sort of design documents, and you say, how do we get from vulnerabilities to usable, beneficial worms? And obviously, the vulnerabilities go through a process at Immunity already. They go from vulnerability to Python exploit, and then, of course, then to a nematode intermediate language, a test framework, and a payload that got deployed. For those of you who read the paper on Witty, one of the things he said was, well, his actual framework for sending out the worm was quite flawed. And he's like, most of these worms are not well tested. And it's just difficult to build a test framework around worms. And that's one of the problems you have to solve. This is the generalized problem space. You can, if you take a patch and you use bindiff on it, you can generate the vulnerability. If you use binnavi on that, you can generate a repro. From there, you go through Canvas to get the exploit. And then for our nematode thing, you get nematodes. And so this is the basic cycle of life. Or cycle of cache, how are you looking at it? The thing about where I stand is that we've been writing exploits for 3 years now to a specified API that I think is a fairly good API, and as time has developed, it's become quite rich. And one of the things about that is that when you initially start the project, you're thinking, well, I just want something that works for exploits, but you're also thinking a little bit ahead. You're saying, what language, what sort of features do I want in a language that can aid me to make this flexible for things I can't think of right now? And Python is the language for that. It has the sort of reflexive introspection, sort of the abilities. The language itself is well designed to use in ways you didn't think about ahead of time, and that's something that we were considering when we did the initial design. And so the entire product is written in Python, including all these sort of network libraries that come in. So you don't call socket.send and then here's a big blob of stuff for Microsoft RPC attacks. You send Microsoft RPC connect, bind, whatever, and that gets all taken care of. So that's a good thing, because that means that you have a base of knowledge that you can look at. And you can say, well, what else do I have that will help me do this? And of course, the built-in assembler and compiler is something that will help you, no matter what you do. A simple example exploit in Python, it looks like that. It's got a makesploit, a no-ops, a stir override, connect to host, run once. And these are going to change for every person who writes their own nematode implementation. This is probably something that they will do, because it's much easier to write your exploit to Canvas than it is to write your exploit to just C and then convert it to something else, like nematodes. Basically, the point I'm trying to make here, which is a little obscure, is that if you have a framework, you then have a database of knowledge. It's not just a collection of scripts that run exploits. It's a database of knowledge that you can then manipulate and transform using automated language of some other kind. So this is our nematode workflow. It is that you can take an exploit, convert it to an intermediate language, run it through a testing harness, run it through a specialized compiler, and a launcher. So this is the kind of workflow we envisioned. We have this nematode intermediate language that obviously is under heavy development and is simply a specialized assembly for worms. We already have an intermediate language that we use for the C compiler, and we didn't feel that that was going to be a good representation for what worms need to know. There's just a different set of state that you need to keep. And we wanted something that also was not too hard to parse with PyLex and PyYak, but which right now I don't even bother to use. And again, if you really wanted, you could write your exploits directly to nematode intermediate language. And what you really end up doing is you write them in Python, you test them in Python, you make them reliable, and then you convert them to nematode intermediate language, and maybe you modify them if you feel lucky. So I guess the interesting thing is, how do you transform a good Python exploit into a nematode intermediate language? And we simply, it's actually quite small and easy when you have the right language. You just override the internal API, and instead of generating socket calls and things, you generate prints that print out nematode intermediate language. And of course, you've replaced various structures within that class that, like the shellcode, we don't need that. We're going to replace that with a string, stuff like that. So quite easy to do. I think you could probably do it in C#. I don't know if you could do it in Java. You could probably do it in Ruby, but you probably can't do it in Perl. So this is, we wanted to make it this easy. I wanted to say, I just wrote an exploit. I spent 2 days doing it. How do I make that a nematode, right now? And this is it. Because eventually it's going to get all built into the framework. It'll be a nice little GUI and stuff. So, all right, that's right. My mouse broke like 5 seconds before the presentation. But, for example, this is me down here. I'll hit enter a couple times. That didn't help. And I say, demo exploit's just a canvas exploit like any other. It's a really boring one. You just run it. Do you guys believe me that demo exploit would work? Because I can demo the exploit itself working. But in any case, instead of working this time, it generates this little string here, or this set of strings. It says, I have 5,000 no-ops, I do 2 mem copies. Just overwrites like a mem copy. I start the loop, I connect, send the data, I close the loop, or close the socket, and I end the loop. So it's a very, very simple thing. And it's human readable for sanity's sake, so that you can say, I don't think that looks right. But this is the worm, this is just a sort of recompilation of the exploit. That was an amazing demo, wasn't it? You're like, okay, so I have theoretically solved the problem of going from a demo exploit to a worm. And obviously this problem, as you scale up to more complex exploits, does get harder. And you're going to need to add in maybe some other statements to your worm assembly. But I think in general, I just want to demonstrate how to do this in 10 lines or less. So we also have an interpreter that just reads this stuff in and just interprets it. It just says, well, it said 5,000 no-ops, here's a string of 5,000 no-ops, and it sort of interprets what the framework will do later when it's actually running on the target. And this is what you use to test your exploit in the nematode format. You say, now that I've run it in the nematode format, do you still even work? And typically all your shellcode does is hit int 3, and then you say, hey, it worked. Cool. I would do a demo, but that's even more boring than the last demo. So then you're like, well, okay, those were the easy problems. I've taken an exploit, I've transformed it into an intermediate language. I then need to build the final payload that goes from the intermediate language to basically an assembly payload. And this requires a specialized compiler that I used handwritten assembly, but you could always do it some other way. And then you inject this assembly that you've compiled up into your test framework, send it to the host, and watch it go. So we're going to see an amazing assembly demo now. So nematode, x86 shellcode generator. I think, in fact, I have the source for this on the next page. So don't read the slide, but over here on the right is just a quick transformation of the intermediate language into our specialized compiler. We're adding these attributes to the compiler, and we're saying, at the end of it, just give us the bytecodes that would represent that. So it's quite a simple, straightforward step. We're not like confusing anybody. It's like we go from point A to point B to point C, and here we are. So, and this is the assembly code that it would generate. So you can see that it is something that, I don't know if you can actually read that, but it's quite simple stuff, right? You would recognize it if you were a Linux assembly person. And I wrote it in like a couple hours, so it's not optimized in any fashion. But it's nice to have all the debugging statements there and all the other stuff, and be able to really use an assembler to figure out things like, let me show you the hardest bit here in a second. There is a hard bit that goes into this. And actually, it is a subtract that is difficult. This bit here, right, is of my worm. But I need to figure that out before I've written my worm. So it's a little catch-22 that you let the assembler solve for you with multiple passes. And of course we do. And most assemblers will do 2 passes. We do sort of an n number of passes to try to optimize for size. So that's the assembly code, which was fascinating. But there's also the worm itself over here. For those of you who didn't see me do this, we simply listen on a port and we send it to my little demo vuln, which is it's just basically a mem copy into a 5,000 byte buffer, which overflows quite nicely. I think it's a 1024 byte buffer that it reads in 5,000. Over here, we're using strace plus a little awk script to attach to it, so we can see if it does any system calls. Right now, you can see it's just reading on standard in, and it's not completed. I think that's big enough to actually see. So we do our nem interpreter, and we do out.m, and we then do anything, because that's how I wrote the program. And we run it, boom, it sends the data. And you can see here that what it's now doing is trying to connect and send to other IPs. It's going to time out in a few seconds and send up one more. So it's just sending to 152.2. Actually, let's do this again, because I want to actually show it actually sending the data with a host it can find. So let's see that. Boom. So there you can see it actually did manage to construct and send a little string very similar to the one I sent to it that has shellcode in it and would also exploit a machine. So the magic trick here is that you can take an exploit and in 5 seconds, or depending on how fast you can type, create a worm that you can specify down to some very interesting little blocks. You have a lot of options. So that's the worm actually working. You can see it's saying, oh, I can't reach these hosts, and it's going to just continue going up in number. Now it's up to 14. Obviously, it's got an extremely random way of finding hosts. So that is that. And that was pretty cool, I thought. Okay, so how did we do that? I mean, just to revisit, we have a sort of prelude that we tack on to the beginning of any sort of nematode. We have all the arguments that came in from the code are going to get directly translated into this simple language here. The problems that we're solving here, we need a unified function table. So when you add an attribute, you can say, I require the ability to use memcopy, and it only includes memcopy once. Or you need to resolve a function in some portable executable file and says, well, I can resolve that once instead of having to deal with this later. You need to avoid bad characters. There's a lot of problems that are very specific to exploits. The bad characters problem you can solve in a number of different ways using a specialized compiler. I solved it by writing a demo exploit that had no bad characters. And of course, you want to minimize space because you're writing something that conceivably needs complex operations to happen, and it needs them to happen in 1,500 bytes. So this is something that I think is definitely something you're going to be solving. as you can see, the exploit itself is fairly trivial. And it really does take less than 5 minutes to go from the exploit to the worm. And once we've done that, we really have a lot more opportunity at our fingertips. I think there's a lot of things that are good about that. The worm itself that we just wrote is less than 280 bytes, and a lot of that's because I'm like the worst assembly writer you've ever met, and I just don't care, and I'll write big assembly all day. Obviously there's no real payload in this, it just replicates, but that's what most worms do, so I figured it was reasonably representative of target audience. And of course we have a simple incrementing scanner. You could use some more advanced host finders, or use devu random or something. This is the sort of structure that the compiler creates. It creates its own little binary format. An optional decoder, in this case we don't use one. The prelude, which is responsible for maintaining the state. At the very beginning of a worm, you have a very specified state. It's the state of the shellcode being able to run a worm, because this is the shellcode that did work for the exploit. So you need to save that off somewhere else using memcopy or by simply saving the location if you're not self-modifying. But if you are self-modifying, then your prelude's going to have some work to do. The decoder can be any of your x86 decoders that you use all day long, every day. The body is going to have your actual payload. In this case, it's just a loop that connects them more and sends the data. The function tables and sort of import tables that you build on the fly, and of course your state table, which is going to be different for every instance of the worm. And this is the key factor to making nematodes, is that you have a state table. I think as we do this in the future, there's some things you can do with Microsoft RPC. I think we could build our own minimized type def library and do those as well. The socket issues get different. And what I'm saying basically is, although some exploits require the complex use of libraries, in many cases this is not going to be a problem, because you can subvert the actual functionality that the application has built in. And of course you can do multi-stage worms to get a whole ton of space. You can say, first you listen on a port, and then I send you a ton of data, and then that's your payload. That's going to be less reliable due to natting and things like that, and I didn't want to deal with it, so there's that. I think one key factor, and I think it opened up a lot of people's eyes, was this witty worm that came out, because it made everyone cry and moan. They were like, wow, how could it have come out so fast? And it worked so well, it was so polished. Someone like a genius must have written it, like an idiot savant of the worm writing world, right? And I think witty is just nearly identical to the one I just did in 5 minutes. So I think people need to reconsider whether or not there's a perfectly good worm compiler that someone wrote 5 years ago that we just haven't heard about yet. I think one of the key things about a lot of the research we do is we very rarely think we're doing anything original. A lot of this, you do this for a long time, and then eventually you realize that there are people out there who are just as smart as you, and if you stop looking down on them, you might learn a thing or two. And a lot of them have already written the things you're trying to do. So I think I probably could have handwritten this particular worm in 2 days. And I think there's a lot of people who could have handwritten witty in 2 days, and I just think they didn't bother. And I think as you make this a business sort of solution, you need to make it as easy as point and click. You need to make it so your quality pen testers can do something reliable that they know will work. And only until they know it will work will they really use it. And this is the sort of solution to this. And of course, I think, if you haven't reconsidered how people are doing these worms, then now's a good time. I think there's some really interesting stuff going on with sort of automatically generating worm signatures. I don't know if that's worthwhile or not, but if you're interested in this sort of speed aspect, if people think of this as a race, I like to think of it as a race that you don't get to start till everyone else already finishes. But if you think of it as a race, if that is your broken mindset, then you need to read these papers. Now we've created worms, but we really want to create our nematodes. And so we've kind of been building a basis for this. How can we control this thing? It's important that we can create these things. One option is to have a whitelist, but whitelists are very dumb. And they're very easy to implement, but they're quite stupid. And when you start working with it, what you realize is what you need is sort of a graph. You need a white graph. I need to say that I'm allowed to attack, my wife's laptop, but only from my laptop. Because only from my network is my wife's laptop really my wife's laptop. If I'm on a customer site, they might be sharing her IP, and that's probably not something I want to hit. So you need a simple graph walking algorithm and shellcode, and these are the sorts of things that you can build a language to do for you. Sorry about that, guys. So again, you're going to want wildcards in your graph language. You're going to want, you're going to want a specialized sort of nematode compiler that sort of builds this state for you. It's a little graph that you're walking around as your worm travels. And of course, I mean, there's other uses for doing this. I mean, people are using network telescopes all the time. And I think, you could black graph them, if you will. And the payload that people are, thinking, the minute you suggest this to someone who's serious about using it, they're like, yes, I need to install this management agent, I need to install the patch and reboot, and then I need to report this to a central server. And, I think that's great for now, but I know that as we start building this technology, people will come to us and say, and I need it to make coffee and fly my plane and like, rub my feet. And I think that's the cool thing about building a language that's flexible and sort of powerful, is that you can have opportunity to really build it into other things that you think up later, or someone else thinks up who's smarter than you. So I think these are my testaments to you, and you as a crowd will decide whether or not you agree. I think that you can solve the am I allowed to attack this? I think you can solve the control and command, because we've solved the control and command for a lot of other things, and I think we can do it for this. I think if you have a large library of exploits, then it's more than just a library of exploits. The library of vulnerability data that's formatted in a particular way and is parsable by particular things. And that's a valuable thing for doing this sort of automatically. And I think the generalized techniques that we developed to do what you saw today in our netcaddy demos, I mean that technique is completely cross-platform if you want to make it so, and I'm sure we will later. I believe the next talker is the guy who runs the Worm blog. So I think it's a good resource to keep track of these things, because a lot of times these papers get published in journals that you would never read because the average academic journal in security is not worth reading. So instead, you kind of find the worthy ones, which is good. That's what a blog is for. There's this Worm 2005 academic conference at George Mason, which is November 1st. And they have a bunch of papers that you can already access if you want to. So you don't have to go to George Mason in the world's most boring suburb of Virginia to kind of talk to the authors if you don't want to. You can just read what they wrote. There's this Journal of Computer Virology. I don't know how far that's gotten, but I think it's something interesting to look for, and I think they've started doing. They're more interested in they're much more flexibly oriented. When you talk to sort of the academic community, they're like, oh, can't even think of that. It's too painful to think about, and that's just not the attitude you need to have when you're building new technologies. So the Journal of Computer Virology people seem to be much more cool. And so this is the section where you guys get to ask questions and get me back for any bad jokes that I made. So feel free to ask a question. I'm not going to auction anything off for asking questions, because this isn't Japan. I know people ask questions. Except for at this talk, apparently.
What about the issues of applying patches randomly, for example, without actually testing what the impact on the system is, or the reliability of the patch on multiple platforms?
So his question was, I'm going to do a weird thing for this conference, which is to repeat the question. His question was, if I understood it correctly, what about the reliability issues of the patches themselves? I mean, when I install a patch that, DOS is the box, that makes me very unpopular among my users. And I think what we're seeing is that people don't care. They're like, yes, the patch sucks, but what sucks a lot more is constantly scanning my network. See, that annoys me, whereas the patch sucking only annoys you. Does that make sense? So I think what people do is they say, our problems are more important than your problems, and you're on my network and I have legal mandate. So if the patch, for whatever reason, causes you some slight problems, I've made the value judgment that that's probably better for the network as a whole than you being able to infect thousands of people. And I think this is the sort of thing you're going to start seeing ISPs roll out on a very wide basis, and entire countries. You're going to see Malaysia's government roll out, you know, we need to make this worm go away. Boom, now the worm goes away. And then it stops. That's my opinion, we'll see. Some other brave soul will ask a question.
Dave?
Yes?
I think it was slide 17, you mentioned, one of the problems that you mentioned was you don't see hosts come and go, right? If you scan, say, once a week, on Monday morning, or something like that, you don't see hosts come and go, right? Because if you scan on Monday and IP is, you know, and an IP is not in use, but on Tuesday I walk in with my laptop,
Right.
I assume an IP, and I'm infected or I'm vulnerable or whatever, you missed it.
Right.
Because I'm there just Tuesday, and I'm not there on Monday when you scan.
Right.
What about a passive system that just simply listens for network usage?
Okay, so what he's saying is, what about my company's system, which is a passive system that listens for usage? And I work at Arbor Networks, and we're quite cost-effective, by the way. I think, yeah. What about a passive system? And that.
I'm just curious about your thoughts there. I mean, seriously.
I think passive systems are interesting. I don't think they've proved themselves in the network yet, but that could be because I don't own an Arbor system. So I don't know. I think there's a lot of interesting technology coming out and starting to get deployed. I think certainly that you know, what we have now is definitely too expensive and not solving the problem. We're just not happy. Patching was retarded in the first place, and we're certainly not happy with the fact that every time I patch, it costs me $1 million, because that's not good, right? So that can't be right, and I'm owned anyway. So how did that help me? And so maybe, you know, you start working towards things. You know, I'm sure I'll look forward to your talk in a few minutes, and we'll see.
What about things like Cisco's NAP or Microsoft's NAP program, the network emissions protocols and control systems?
Yeah, I think the next question was, what about Microsoft and Cisco, who built these sort of network intelligence systems that do other things? And I think, yeah, you're starting to see people start pushing sort of, you know, all sorts of crazy stuff out to the switches to say, now I need to hook into that. So every time anyone connects a new machine, you know, pop me up a message, you know, via, you know, XML RPC, and then I will scan it. But I think yeah, that's some, you know, you want more intelligence in your switch to do that, but I don't think that's going to solve your problem. I think it's going to be interesting. And maybe you solve part of your problem with that. Maybe you hook that into something like this. So that's good questions. All right.
So here, microphone works now. You mentioned that you are actually compiling the code into assembly language. So can I expect that your worm system only delivers binaries to the target system where the worm's actually running it?
Right. Yeah, we actually, maybe I explained that extremely poorly. That's probably because my mouse is broken and I'm really mad about that. But this sort of, you see a sort of assembly here, and then when I type .get, or when the code ran .get, so this data equals, actually they gave me this, which is cool. See that? The data equals nem.get actually we'll assemble it, do the special compilation stuff, make a binary blob out of it, and that's your new shellcode. So then you use your shellcode, and then if you look at this says CC the shellcode. That's a special string, and when the interpreter goes through it and you've told it that you actually want to run a payload, it just replaces this string with the payload that you told it to replace it with. Does that make sense?
Yeah, well, in simple steps, if I want to secure my network using this nematodes, how you call it, I sort of think that I have heard the word agent 10 years ago already. Is more or less describing the same concept. But what are the basic steps one has to take to make advantage of these worms, and how do they distribute? Are they attacking my own systems to distribute, or?
All right. So I think the first thing is that this talk is not about, like, to build that tool, you go from the exploit, you have an intermediate language that gets created from an exploit. It then goes through a testing harness so you can make it reliable, which is a key factor in you being able to secure your network, is having a reliable exploit that you can deploy like this. You run it through the nematode compiler, and then you have a launcher. And at the point where you have a launcher, you've now already got binary. But the point where you're making it something flexible that you can use is basically at the exploit to intermediate language stage. I can click a little option that says, instead of just hitting random hosts, hit only hosts that will respond to the following, friend or foe system. And once you've hit that host, I want you to include this payload. And this payload I've specified as part of the intermediate language that says, I need you to download and install this patch. And you may download it from the worm network itself, via whatever P2P network algorithm you've written in 500 bytes or less. Does that make more sense? Or did I make it even more money?
It makes more sense. I couldn't go into indefinite details here now.
Okay, you can always find me later. Or you could, whatever that's on that list, you got like a book.
Do you, this could be interesting. Is there any, do you plan any kind of code distribution? Is any of your products being, destined to go on the net and being used by anybody, like the nil intermediate language compiler also?
I mean, you just saw it all, so there you go. I don't think it's necessary. I mean, once we deliver the concepts, I mean, I definitely think people are smarter than me, and they can write this up in, less time than I took to write it up. But I got a good flight to Malaysia, so booyah on them. The thing about this sort of thing is that it's not, the concepts are simple, and I think everyone will have their own implementation, and we're not at a stage yet where we're putting it in our products. But that's when you'll start seeing it, is when we start delivering it as a service. That's something you can really use.
Okay, thanks.
So, like the rest of us. Cool. Well, I think that's probably about it. You can always see me later and ask me much more complex questions. But I hope you guys enjoyed it, and I hope that you will write your own. And that is it.